Hi, y'all. We're excited to have you here and want to welcome you to Flatiron School's Intro to Data Science, Understanding Decision Trees. My name is Corey Mickelson, and I'm the event coordinator here with Flatiron School. A big part of my job is hosting these introductory workshops like this afternoon's event, and to give you all an opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. So a quick little reminder, we're going to be using the chat tonight for our main source of communication. So make sure you set that little blue button from host and panelist to everyone so we can all chat together. Without further ado, I'd like to introduce our host for the afternoon, Mark Barber. He is one of our fabulous data science instructors. Go ahead and take it away, Mark.
Hello. Well, I'll go ahead and get started with the slides, and I will share a link to them real quick as well. I'll put that in the chat. So feel free to download those, follow along, and this will also have some links inside of it that will link to other resources I'm using, like a GitHub repo and a couple of interesting articles from Wikipedia. So a little bit about me. I'm a data science instructor here at Flatiron School. I've been here since October of last year, so I just surpassed my 1 year with Flatiron. Before that, I was running my own data science consultancy. I did that for about 4 or so years, but I actually started my career as an information worker, as a 911 dispatcher. A lot of people don't realize how heavily you rely on technology as a dispatcher, but you can imagine while I was there, you're basically responsible for 3 different computers. So 3 different keyboards, 3 different mice, 7 different monitors, a phone in one ear, a radio in the other, and a foot pedal to operate the radio. So you're very plugged into technology in that role. After 5 or so years of being there, I became increasingly more interested in the technology side of it. How we make software that allows people to dispatch and respond to emergency calls. As I kind of progressed my interest more and more in the IT side of things, I got a couple of IT certifications and started consulting for companies like banks and real estate firms and title companies, and was doing pretty much all kinds of general IT stuff. I started out just kind of with the simple things, doing desktop maintenance and support, and then kind of progressed in my career and started doing more project management, a lot of kind of large system technology implementation. So Wi-Fi system, like enterprise grade Wi-Fi systems, VoIP systems, security systems, server maintenance and support, server installations, building networks, maintaining networks, cybersecurity, all kinds of stuff, until I started heading more towards specifically data center operations, and kind of decided that I didn't want to spend my career crawling around under the floor in these, like, below these dusty server racks, and had the opportunity to start focusing more on data science and programming. And then as a data science consultant, I've primarily worked on a lot of computer vision systems, some AI security implementations. So on existing like video security systems, doing real-time search and alert for facial recognition, weapons detection, fire detection, anomalous behavior detection like falling or fighting or stuff like that. I've done a little bit of photogrammetry, so measuring things with pictures. One of my clients was measuring garments with phone cameras. Another one of my clients was doing 3D modeling of telecoms infrastructure, and did a little bit of classification for that in terms of like identifying equipment and all kinds of interesting stuff. And I've also done a little bit in education. Primarily, a lot of that was just volunteering and being an advocate for code and data literacy. And of course, now my kind of full-time job here with Flatiron is all about education, since I'm a data science instructor. So I kind of bring people into the fold of modern code and data literacy, and it's a lot of fun. So the agenda today, we're going to do a quick game that's related to how decision trees work. I'll introduce you to trees and some of the language we use to describe them. We'll talk a little bit about how a computer does this, and then I'll kind of solidify that with an example. We'll get into a notebook, which you guys will all be able to take a copy of. And don't worry, you don't have to have a programming environment set up locally. You don't have to worry about touching the command line or anything scary like that. Although it's not too scary. It's once you learn it, it's quite useful. But we'll be doing everything in Google Colab, which Google is nice enough to do all of that that dirty technical work for you. And they just give you a nice little notebook, and you'll be able to take that from my GitHub and copy that over, and you can save that and you can tinker around with it, make tons of errors, break things, fix things, and hopefully find some use out of it. We'll go over some pros and cons of decision trees, and we'll talk about certain cases where you'd want to use them. So game time, we're going to play 20 questions real quick. I've come up with an object that I've kind of written off to the side in my my text editor. These are going to be just yes or no questions. So you guys will use the chat to ask your questions, your 20 questions, and I'll do my best to kind of write them down. And then we'll see if you guys can guess my my objects. Let me escape here. So go ahead and take a second now. I've already got the item written down, and I'll show that to you at the end. But yeah, go ahead and someone ask the first question, and I'll give you a yes or no. Oh, and actually, Ray asked a question just prior to that. To use decision trees, do you need to scale the inputs or outputs as you usually do with neural networks? You can. I mean, scaling is, a lot of times it kind of depends on the data. So like, let's say you have a bunch of data that is all kinds of different scales, right? Like, let's say you have a bunch of data about cars, and you have things like their gross vehicle weight, how many doors they have, their top speed, their fuel efficiency, right? So the number of doors is going to be a single order of magnitude, right? Maybe 2, maybe 4, maybe 5. Or like the number of cylinders, it could be a 4-cylinder, 6-cylinder, 8-cylinder. But then you've got things like gross vehicle weight, which is in the thousands. And so what can happen is if you use certain algorithms, then the numbers that are higher are going to have a much greater weight in terms of influencing the algorithm. So we scale things down so that they're all kind of on the same order of magnitude. You can do that with decision trees. One of the benefits is you don't have to. Decision trees do pretty well with unscaled data or imbalanced data and things like that. Okay, so we've got some of these questions here. Thanks for the question, Ray. It gave people some time to put their 20 questions in. So is it smaller than a fist? Is it smaller than a fist? No, it is not. And then we have, let's see here. Is it live? Is it live? No, it is not. It is an inanimate object. Is it live? And I'll kind of compress the similar questions down because we have, is it living as well? So I'll kind of include that as the same one. Is it a common household item? Ooh, I guess it depends on where you live, but I'm gonna err on the side of no. So is it a common household item? And I'm gonna say no for that one, and then no for that one. Let's see here. Let's see. Does it have any sort of intelligence? Is it smart? No. So any intelligence. No. All right. Can you eat it? I mean, you'd have a rough morning, so I wouldn't advise it. I'll go ahead and say no on that one. Can you eat it? No. Let's see here. Is it a tool? Is it a tool? It's more, I'll say no on that one. It's more of a recreational thing. Does it belong outdoors? Yes, it does. It belong outdoors. It'd be very hard to use this object indoors. Is it electronic? No, it is not. And it doesn't run on electricity. You don't have to charge it. Doesn't plug in or anything like that. Does it use electricity? No, it does not. Can it move? Yes, but not on its own. But it is designed to move. And Let's see here. Do you smoke it? Again, it's probably going to be pretty rough on your body if you do. But I'm going to say no for that one, just for health and safety reasons. Is it heavy? It can be. It depends. I'll give you a little bit of a hint there. If it's really windy, then yeah, the weight of it can become a little cumbersome. So I'll say yes for that one, but it depends on kind of what scale are you thinking, right? A piece of commercial equipment like a crane, if you think that's heavy, then this wouldn't be heavy, but we'll just kind of keep it in the scale of what humans can handle and manipulate. Does it bounce? No, it does not bounce. Does it bounce? No. All right. Is it round? It is not round. It's actually, someone had asked the shape earlier. I'll go ahead and give you another clue. It's more kind of like oval or oblong type of shape. So is it round? Say no to that one. Is it a car? It is not a car. Although, well, man, that one. I'll give you a hint that it's a vehicle of some sort. It does not have wheels. It can be made of plastic. Does it have wheels? No. Is it made of plastic? Yes, it can be, but it's made out of a wide variety of different materials. But you can find many examples of ones that are made of plastic. Let's see here. Is it fuzzy? No, it's not fuzzy. Is it fuzzy? Let's see here. Does it have a handle? Not ones that I've seen. Can you get on it? Yes, you can. The whole point of it is you can get on it. Let's see here. Can you get on it? Yes, you can. And let's see here. Is it more than 3 feet tall? Oh, we got tons of questions in here. I'll do, let's see. Can it hold a person? I kind of answered that one. Do you use it in water? I'll use that one. Okay. Do you use it in water? The answer to that is yes. So that's our 20 questions. So I'm going to scroll down and see. Yes. And we have Laya and Salil. And if I mispronounce your name, apology. What I was thinking of is, of course, a surfboard. So you kind of have this idea of going through and having some object or some data and being able to ask questions about that thing and get some information about it. And that's kind of the basis of decision trees. So thank you all for your participation and your questions. And of course, those of you that guessed as well. So yeah, the object I was thinking about was a surfboard. It's definitely not smaller than a fist. It's not live, or at least any that I've ridden. This is a common household item. You see them a lot if you live by the coast, but otherwise not so much. Any intelligence to it? I haven't seen any smart surfboards yet, so no on that one. Again, you can try to eat it, but I don't know how good fiberglass is for your digestion. Is it a tool? I said no. I was kind of on the fence of this one because, again, you can use anything as a tool, right? But in general, people use it recreationally. Does it belong outdoors? Absolutely. I do not do any surfing in my living room. I have to do all of that out on the ocean. And of course, it doesn't use electricity. The whole purpose that it moves, again, it might be pretty rough to be smoking fiberglass, so you can't smoke it. It is heavy, and again, it depends on what scale you're thinking, but when you're trying to like fight waves and you just you ate it really hard and you've got like all kinds of shells and sand in your wetsuit and you're trying to pick that thing up out of the water and it's nice and windy, yeah, it can get a little heavy, a little cumbersome, right? Doesn't bounce, unfortunately. If you throw a surfboard into the ground, you'll probably damage it. It is not round, it's kind of more oblong shape. Definitely not a car, no wheels, but they can be made of plastic, right? You can get those kind of beginner foam boards, which are a lot more fun, but they're a little less agile. Doesn't have wheels, made of plastic. It's not fuzzy, doesn't have a handle. Definitely want to get on it. Staying on it can be a little bit of a trick. And then of course you use it in water. So you kind of get this idea of, oh, see, someone's already linked a smart surfboard here. Yeah, there you go. So yeah, some of them I guess are intelligent, but I think that's a thing that we have to all start getting used to. When you're toaster starts greeting you in the morning. It's kind of the world we live in now. But yeah, so you get the idea here, right? You can have these systems that provide a lot of information. We can gather that information about them and preserve that information as data. We can ask questions of our data, and we can kind of figure out more information about that. So that kind of relates to decision trees, because again, we have some system that we want to measure or capture data about, and we want to try to understand or acquire knowledge from that system using that data. So if we have this, oops, there we go. If we have a table of data here, let me make sure I didn't miss any other questions. I think I saw one other that was outside of the context. Oh, okay. So Edward asked, are modern decision trees different from when they were introduced in the 1950s? Fundamentally, no. The algorithms haven't changed much. I mean, there's other algorithms that we've built from that. They get used a lot in ensemble methods. So we'll talk very briefly about things like random forests. But the big change with respect to data, or with respect to decision trees, is the computation that we now have to process data, and of course the massive amounts of data that we have at our disposal. So those are really the only big modern changes to decision trees themselves. But it's a great question. Thank you for asking. And then, so let's say we have some data about whether we're going to go out and play a sport, or maybe whether we're going to go play tennis or surf or something like that, right? And we've kind of documented whether we've made that decision in the past. So, we took some data down about the weather. It was sunny, it was hot, the humidity was high, and it wasn't very windy. Were we going to go out and play? No, we didn't. It was cloudy, hot, and the humidity is high, and the wind is weak. Then yeah, we might go out and play, and so on and so forth, right? So the idea of a decision tree is it's a lossless compression of information, so that instead of having to try to go through and look at several different conditions and say, hey, what are these conditions, and did I play that day or not? And if these are similar conditions, should I go out and play today or not? We can compress that down into a decision tree, and that will allow us to then ask a series of sequential questions that arrives at the answer, rather than having to consider multiple columns simultaneously. And as a result, this is a lot easier for humans to interpret, but it's also a lot easier for computers to interpret. It saves a lot of computation. It saves a lot of memory. Asim asks, can they not result in false positives, and how do you resolve to get to the right answer? So any model, and this is actually a great question, because this is a very, very important concept in any kind of statistics, data science, machine learning, AI. All models are bad. Some are useful, right? And a lot of times when you're doing these sorts of things, you don't want to make perfect the enemy of good enough. If you get to a point where a model is useful, it saves time, it saves money, it has a great explanatory capacity, it has a great forecasting or predictive capacity, that's kind of that's more of what you want to consider, rather than, if it has any false positives, false negatives, anything like that. So any model is going to result in some level of false positives and false negatives. And there's a lot that you're going to do to kind of find out how often that error occurs. And we'll talk a little bit about that with like confusion matrices and stuff like that. So every model you're going to get is going to have some flaws to it, but the question is whether it's useful. So in this case, we have this table, we've compressed this down into a decision tree. You'll notice that temperature is conveniently missing from this, but the way this gets broken down, right, is we kind of pick one primary question and we look at all the unique values in that data, right? And we can see that we have a lot of different rows here, but primarily it's either going to be sunny, cloudy, or rainy, and that breaks out into the edges of our decision tree. And in this case, if it's cloudy, right, we consult our table and we look at whether it's cloudy or not. In every single case, it's cloudy. We went and played, regardless of what these other columns are doing. So you can see this just terminates right at a leaf here to yes. If it's cloudy, go play. Now, is this a great model? I don't know. There might be other factors, but according to the data, very, very limited sample of data, if it's cloudy, we'll go play, right? If it's sunny, we have to ask more questions, because if we cross-reference sunny, sometimes we don't play and sometimes we do play. So there's a little bit of information there that we have to capture. So we look at these other columns and we say, excluding temperature, mostly because of slide real estate, but we have to look at the humidity. So if it's sunny and the humidity is high, we don't play. So if it's high, we don't play. Or if it's sunny and it's normal, then we do play, right? Or if it's rainy, we have to ask whether it's windy or not, right? And you kind of go through the same process. You go through all of the unique values in a column. You then continue to ask what is dependent on that until you reach an edge or a leaf node and you have your answer. Let's see here. Ray asks, question for later in the lecture. I'll try to address those now, just because I might forget to come back to your question later. So would you expect the decision tree model to always regularly get better results than a regression model? So actually, decision trees can do regression and I'm drawing a blank now. Classification. So you can use decision trees to do regression or classification. But for example, like a linear regression model, it depends again on the data. Decision trees aren't linear models. So it kind of depends on the data whether linear regression would be better suited or decision trees would be better suited, but you can do regression. You can deal with continuous numeric data with decision trees just fine. You might have to change what metric you're looking at. We'll talk a little bit about information gain, Gini coefficients, and greedy algorithms. Very, very briefly, I'll link you to some more resources about that if you're interested. And then the second question is, I have data I'm using, and the decision tree sometimes is better than the regression model. Yeah. And the idea here would be you pick an algorithm that would be appropriate. It's almost kind of like the scientific method, right? You're going to create a hypothesis. You're going to try a model out. You're going to take some metrics, and then you're going to try another model and then get some metrics, and you can compare those metrics. We won't get too much into that today because it gets a little bit technical. But any model you run, you're going to get some metrics from that, and then you're going to compare those metrics and see which model performs better, and that will be the one that you choose. Okay, so yeah. Some of the terminology we already discussed, right? Anywhere you have a decision node of, hey, are we going to do this or are we going to do this? That can break out to another decision node, and you kind of keep going through that until you have no more dependent features and you reach a leaf node, and that's going to derive your answer. That's going to say yes or no or 0 or 1 or whatever the answer is. You can have subtrees where you have things like decision nodes and everything like that. And then it's not labeled here, but these are traditionally just called edges. So you kind of have this graph terminology of nodes and edges and things like that. So how does a computer do this? We talked a little bit about this a couple slides ago. So there's information gain. This is kind of going through those 20 questions. This tends to be better if you're dealing with classification, so you have a bunch of nominal data like we did up here, right? We could have things like humidity being represented by a percentage. We could have wind being represented by knots or kilometers per hour or miles per hour or feet per second or whatever, right? However it's measured, we can use ratio data here, but because we're using nominal data or categorical data, information gain might be better. It is slower to use, but it's going to be bound by a 0 and a 1, a yes or a no. You kind of get to the leaf, and that leaf is going to contain one bit of information. And then you have Gini impurity. This would probably be something you would want to use for a regression task rather than classification. So if instead we had those numbers, maybe instead of weather being sunny or cloudy, we have something like UV index, and then we have the miles per hour for the wind, and maybe we have a percentage of precipitation or how many inches of rain, right? We can use ratio data or numeric data instead, and in that case you'd want to use something like a Gini impurity score. It is a lot faster, and it's bound by a 0 and a 0.5, so it's going to kind of like take the middle of those values and kind of decide one side or the other. And then you have a greedy algorithm. So these tend to make the best choices locally. So we kind of talked about those subtrees. So it's going to kind of make the best decision and kind of all the combinations of subtrees and not necessarily be making the best decision overall for the entire algorithm. And there's going to be, none of these are necessarily better or worse than the others. Again, it just kind of depends on your data, what your application is. You would use, any of these and, take some metrics and you compare those metrics and that will kind of give you the answer of what is best to use here. So I have a Titanic dataset notebook that is on my GitHub. So if you follow, and actually, Corey, if you have those links handy, I might.
I can do that real quick.
Okay, yeah. But it'll basically just be at github.com/my name, Mark-Barber/intro-decision-trees. And that will bring you to a page that, whoopsie. Looks like this. Thank you for adding that, Corey. So if you follow that link and you want to follow along with the code, there's no live coding or anything like that. So don't worry, all the code is included in there. But if you want to copy this and you want to save it for later, you can save this. You can save this link here. And what we're going to be doing. So we've got some data here. I'll kind of briefly look at the data. This is hold on here. My Zoom tools are getting in the way. Let's see here. You can kind of look at the data here. And I always recommend just like looking at the data, right? It's an important step that a lot of people skip. But it's good to just kind of scan and look at some values. You can get an idea of how unique values are. If you have a lot of unique values in a column, whether you're dealing with numeric data or anything like that, if you've got kind of null values, it might be hard to see through my screen here, but I make this a little bigger. You can see, anywhere we have this double commas, we're kind of missing a value here. And, it's kind of the modern day equivalent of watching paint dry. It's not kind of the most stimulating activity, but it's a good step to go through. You're priming your brain about the data itself, right? This is kind of the least abstract part of what you're going to do. And it's good to anchor your attention to the actual data that you're handling. So I like to just skim through and look at it. It tells you how many data you have. So we have 891 rows here. We've got all kinds of names and ages and genders and all that stuff. And so that's a good first step. But how do we actually play around with this? How do we get this into something that we can program and get errors and fix errors and run things and see how it goes? For that, you want to take this green code button here. You want to click on that. And then you're going to click on these two squares here. That's just going to copy this for you. And then the next thing you want to do is you want to go to collab.research.google.com. And this one I can paste in here since it's right here. So collab.research.google.com. And that's, I'll have to go back and copy this again. So copy this. And then you want to go to GitHub. So again, you've got github.com, mark-barber/intro-decision-trees. You want to go to the green code button and click these two squares. And when you go to collab.research.google.com, you'll have some options up here, examples, recent, Google Drive. You want to click on GitHub. Once you click on GitHub, you can just paste this in here and search. And it'll take a second, but this will pop up. And then when you click on this, it will open it in Google Colab for you. Wait a second. That's not right. Hold on here. What happened? Oh, you know what? Maybe try to take this .git off. Let's see what that does. There we go. Okay, so don't use that .git at the end. For some reason, Google is weird about that, but you'll see this decision trees intro IPy and B. So I'll give that a couple seconds. I'm going to read through the chat, just make sure I'm not missing anything. Let's see here. Perfect. Okay. Give it another few seconds. And if you're having trouble with this or it's giving you errors or not loading or anything like that, feel free to let me know in the chat. How are we doing on time? Not too bad. We can spend a little bit of, yeah, absolutely. Okay, so from GitHub, so github.com, mark-barber /intro-decision-trees. And you can find that link up here that Corey was kind enough to post for us. And then it probably would be better to just copy this from up here rather than doing the green button and copying that, because that .get for some reason caused an error. So you want to grab this from the URL itself. And actually, yeah, and that's that same link there. And then when you go to collab.research.google.com, you'll want to paste that in there. If you did use the code button, again, you just want to delete the .get at the end of that, and then hit enter, and it'll kind of load. It might take a second, and then you're going to click on decision trees intro IPy and B, and that will open that up for you. There's also a link to the slides. So it's kind of connected back to the slides. They refer to each other. So if you have the slides or you have the notebook, you can always get back to the rest of the material. Yeah, I'll give it another few seconds. Again, if you have any issues or anything like that, please let me know. And again, we're going to this GitHub link. We're copying the URL. We're going to collab.research.google.com. Clicking on the GitHub button, pasting this in, and then opening decision trees, intro, IPy, and B. All right, so our learning objectives here, we want to explain how a tree is created using Python. We'll build a decision tree model in sklearn. We'll interpret a tree diagram, and then we'll decide whether or not a decision tree is an appropriate model for our given problem. Again, I won't get into a lot of technical stuff. I don't think this gets in any metrics or anything like that. Just kind of showing the code of how this is used and how we can create a decision tree. So we're going to import a couple of libraries first. Most importantly, we need pandas, we need matplotlib, right? We want to be able to visualize things. We want to be able to handle data. We're going to do import pandas as PD, just so that we don't have to type out pandas. Why are we saving 4 keystrokes? Well, in a lot of ways, it's not really about saving keystrokes so much as it is about saving line length. In Python and programming, typically you don't want your lines of code to be too long. You want to be able to kind of have lines under about 80 characters. That's what this vertical line here represents. And you can see that this line of code goes a little beyond that. It's not a hard and fast rule, but if you can save 4 characters on a package that you refer to very often, that's going to make your code a lot more concise, a lot more readable, and help kind of stick within some general Python programming guidelines, which we call PEP 8. So if you're interested, you can Google PEP 8, PEP 8, and that is the kind of what do they call that? The style guide for Python. So we try to truncate things as much as we can. It's a little more apparent when we're trying to get matplotlib.pyplot. We just want to truncate that down to PLT. From sklearn.tree, we're going to import our decision tree classifier. And then actually it looks like we do use some metrics. So we're going to plot a confusion matrix. We're going to use the accuracy score, precision score, recall. Does this actually get into the ROC-AUC? No, it doesn't. We just plot confusion matrix, it looks like. And interesting. Yeah. So some of these, yeah, we won't get into precision recall, ROC-AUC, and the F1 score, but I encourage you to look those things up and get some knowledge about them. This matplotlib inline, this just renders our visualizations in line with the notebook rather than trying to export them. It tends to be a little less buggy in Colab if you run this. And we're going to set some parameters for the figure size and the font size. So we're going to create a 6x4 visualization, and it'll have 14-point font. So you can, just a couple of quick things about Colab. You can add code blocks, you can add text blocks. Text blocks use things like Markdown, so you can have things like headers, different size headers, right? You can have things like bullet points. And if you don't remember the syntax, that's totally fine. You can use these buttons to do things like bold things. Right, if we bold this, you can see it turns out bold, or we can italicize things. And we can see it's now bolded and italicized. You can do things like inline links. So link, I'll just use good old google.com here, right? You can kind of see, you can kind of use Markdown to organize things. And the way I like to think of it is Markdown is a language that has syntax that allows you to add formatting to plain text. So this up here would be the example of plain text, and this would be the example of formatted text. So you can add code blocks, you can add text blocks. If you have a code block, you'll notice these empty square brackets where if I hover over it, it gives us that play button. This keeps track of our execution count. So if you're going along and you get an error one of the things that'll be helpful is to make sure that your execution count is sequential. Because sometimes if you run a code block and you run another one, you go back and run another code block, it might cause an error or something like that. And so knowing the execution count can help. It also tells you whether you've run a cell or not. So for example, if I try to run this cell without running this cell first, oops, actually this is a bad example because it will run. If I try to run this cell without running the prior two, you might get this warning that says, be careful, someone else off in this notebook. That's okay. Yeah, so if I run this and I get something like a name error, for example, this says name PD is not defined, and I'm like, oh man, I got this error. How does, what happened? You can see this execution count is now 1, but if I scroll up, I can see these other execution counts are empty, right? And it's like, okay, that's the problem there. So if you get something that looks like a name error, it can be helpful to just go back. And if you have any of these empty square brackets, it's like, okay, yeah, I missed something. We can run that, and then it'll be good. So if you run into that, again, always feel free to ask questions. I'm happy to help troubleshoot. You shouldn't need to troubleshoot code too much though, because all the code is present. But if you get that name error, that's a quick trick you can try for yourself to see if that works. And yeah, I'll send out. So there's actually a couple links, Sandra. So this is where you would want to start. And then what you'll do is you'll just copy this, and then you'll go to collab.research.google.com. Oops, that didn't show up as a link. So let me do this instead, collab.research.google.com. And when you follow that up, you just want to go to GitHub and you'll paste this link in here. And again, that's that link I just posted, the GitHub link. You'll paste that in there and you'll hit enter and you'll select this decision trees one, and that will open this up for you. Okay, so we've imported some libraries. We've changed some things about our notebook environment so things look good, and we don't have to deal with any kind of weird errors or anything like that. And the next thing we do is we create a quick function that's going to print the metrics for our classification. Now it actually looks like we do use this, so that's good. So we use the def statement to create a function which we're calling print metrics. It takes the Y data, so this is going to be our target, and then it takes the predictions that our model made, and so it's going to compare those and see how wrong our model is, and then based on that metric, we can do accuracy, precision, recall, ROC, and F1. These are all different metrics that you would use depending on whether you care about things like false positives or false negatives or just overall accuracy, or if you need to care about false positives and false negatives, you might use your F1 score. The receiver operator curve kind of plots, how do I explain this? Not technically. It kind of plots how often you got false positives and false negatives, and the AUC stands for area under the curve. So the greater the area under your curve, the better your model is. So these are a handful of different metrics that we use. And in this case, we just print out the text that tells us kind of what it is, and then the actual value that gets generated by our function here. So we want to make sure we run that. And then finally, we want to read in the data, right? This https raw.github user content, blah, blah, blah. All that's referring to is when I went to my data here and I clicked on this and I went to view raw and it brought me to this page. You can see that this web page here ends in a file called Titanic CSV. And that's exactly what this is. It's just comma separated values. It's tabular data that keeps track of an index for all the passengers, whether they survived or not. So the survival, that's going to be our target. 0 is they didn't make it. 1 is they did make it. And then we have all these other features like passenger class, name, sex, age, civ SP. I don't remember what that means. But yeah, basically we have all these other features that describe a little bit of information about the passengers. And then we have this target of whether they survived or not. And that's what we're going to try to predict with our decision tree. So basically this URL here, you can take a CSV from the internet, and you can, in this case, I've made it into a string, and I've stored that in a variable called URL. And now I can just do PD. Again, that refers to my pandas library. So pandas is the rock star here. I'm going to do PD, and I'm going to use the read CSV method, and I'm just going to pass my URL to this. Alternatively, you could just pass this string in directly if you don't want to use the extra kind of variable layer. You can do this, and this is just fine. But basically what it's going to do is when read CSV runs, it's going to unpack this URL. It's going to see, this points to this string, which corresponds to this URL that has the CSV file. Pandas is going to take that, and it's going to return a data frame in a variable called Titanic. And if we want to encode, so if we look at our data here, we want to try to use numbers. It doesn't matter which order you use. We're just going to encode this, so we're dealing more with numbers than text. And I'm actually pretty sure it would work without this step, but I didn't author this notebook, so they might have had a good reason for doing this. But we can use this mapping function, and you can map kind of unique values to, whatever you need to. You can convert them to numbers, or if you want to use uppercase or lowercase, or if you want to truncate things. There's all kinds of things you can do with the map function. But basically, this just takes a dictionary where the value that's matched corresponds to whatever you want to change it to as the value. And we've changed this specifically in the sex column here. So basically right here, we've changed this from the strings to the numbers. And then we can do things like, if we have missing values for the age, we can use the fill NA method, and that will allow us to fill any missing ages that we have with the median value of all of the other ages. And then in place equals true. This is just a quick way of saying, hey, I want to run this method, but I also want to change my data frame in place. I want it to run and change the values that are actually in the data frame, as opposed to just looking at, what it would look like if you run this. It'll just kind of show you what it does rather than actually changing your data. So if you want to see what your change looks like before you commit to it, you would do in place equals false, which is also the default. Or if you want to sit, and after you've looked at it and said, yeah, this is right, you can do in place equals true, and that will write your changes to your data frame. We're going to create a data frame of dummy variables for the rest of our categorical values. So pd.getDummies, we're going to turn embarked. So if we look at our data here, embarked is going to be either S or C. And actually, I think the slides. Yeah, here we go. Okay, so our survival, this is our target. We've changed this to 0 for no, 1 for yes. Passenger class, we've changed first, second, and third to 1, 2, and 3. We changed the sex. The age is already a number. The ticket's already a number. The fare is already a number. The cabin's already a number. And embarked is going to be C for Cherbourg, Q for Queenstown, and S for Southampton. And again, we're going to one-hot encode that. So we're dealing with numeric data. And then we are going to drop any, let's see, what is this doing? Embarked, dummies, columns. Yes, we want to drop one of these. And the reason why is, I'll explain this non-technically. That's a tougher one. Basically, it comes down to so we don't want to have redundant information, right? And if we create our dummy variables here, so if we have one of 3 possible outcomes, if we have C, Q, or S, we don't need 3 new columns to represent that. We only need 2. And the reason why is because if it's not C or if it's not Q, then it has to be S, right? It's going to be one of those things. Why not explain it technically? Just because it's a little less helpful, but I think that works, right? The idea here is if you have only 3 unique values in a column and you break that out into dummy variables, so that's essentially what this get dummies does, is instead of dealing with S or C or Q, we're going to use embarked Q and embarked S, but we don't need embarked C because only one of these is going to be hot. And that's what one hot encoding means, right? So if you have the option between Q and S and C, and either Q is 1 or S is 1, then C is going to be 0. But if Q is 0 and S is 0, like for example, in this second or this passenger ID 2, we know that they embarked at C. So we don't, but if we add that third column in, it's gonna kind of duplicate the information, and that might cause some overfitting. And we'll talk about problems with decision trees a little later, overfitting, underfitting, things like that. But yeah, so I think that's the best way to explain it. But if that's confusing, again, feel free to answer questions, and I'm happy to answer them. So that's what Get Dummies does. That's why we're dropping this one. And it doesn't matter which one we drop, right? A lot of times as a data scientist, you're going to make arbitrary decisions. It doesn't really have a huge effect as long as you document what you're doing. And in this case, we didn't, because this is kind of a learning model. But yeah, we could have either dropped 0, 1, or 2. Doesn't matter which one. We just need to make sure that we drop one of those options so that we're not duplicating the information in our model. And again, that can lead to overfitting. We're going to concatenate this. So we're taking our Titanic data frame, which has kind of all the original categorical values before we did our one-hot encoding with our Get Dummies. And then we have our embarked dummies, which is all of our, actually, I'll just show you this. So if I add a code block here, if we just look at embarked dummies, you can see that this is just the Q and the S. But we want to, and if I look at, where's the other one? Yeah, if I look at Titanic, actually, this is up here, or was. Oh yeah, I'll just call it here, Titanic. If we look at this, you can, well, yeah, I've already changed it. If you look at this prior to the change, all you would see would be passenger ID all the way up through embarked with the original categorical data. And then we kind of stitched our embarked dummies. So the embarked Q and the embarked S, we stitched that on the end here using this concat. So concat means concatenate. Basically, we're just taking two things and we're stitching them together. What we're stitching together, we pass as a list. So we have these two data frames, Titanic and embarked dummies. And we're gonna stitch those two together. We're gonna stitch it axis equals 1, right? That tells pandas the direction that you want to stitch things in. The way I remember this is 1 is vertical and so are columns. So if you use axis 1, you're gonna stitch it together column wise. If you do axis equals 0, that's like an O in row, you're gonna stitch it together row wise, right? So axis equals 1 is what we want to do here, because we want to add those new columns that we created to represent our categorical embarked column. We want to stitch that to the end column wise. So we're going to do axis equals 1. And then Titanic.head. Head just gives us a sample, by default 5, but you can pass whatever number you want here, right? And then maybe except really, really large numbers, but Titanic.head of 10 is going to give us a sample of 10. We can do 5. And we see we only get 5 here, and 5 is the default, so you don't have to actually provide that information, and it will give you 5 by default. And now we see we have our passenger ID, we have whether they survived or not, we have their class, we have their name, we have their sex, age, and so on and so forth. And actually, what was that SIB BP? I don't think they include that in here. I don't know. Maybe that should be dropped. I'm not sure what it means, but it's in there. So yeah, we have our cleaned up data frame that we will be using for our modeling. A lot of times, if you have null values, your modeling will just raise an error and say, I can't do anything with null values. So you have to kind of do that data cleaning as a step pretty typically. Then we're going to define our X and our Y. So our X are going to be our input columns that we're using to make our prediction, and our Y is going to be the thing that we're trying to predict. So just like we talked about here, survival, this is our target. The target is the thing that we're trying to predict, right? Given all these other features, we want to be able to determine what the target is, whether they survived or whether they didn't. So in this case, we're going to define a variable called feature columns. This is just going to be a list of strings where these strings match the value that we want to use, the things that we kind of assume are going to be most relevant. A lot of times this can be very iterative. You start with a handful of features, you run some modeling, you do some metrics, and maybe you can improve your metrics if you look at different features in your data. But we're going to start with these, and we use this big X notation. This is a linear algebra convention. Big X is your features, right? This is kind of your input matrix. And then your Y is going to be your target. And we'll look at Titanic.survived. And all this .survived does is it looks, if this matches the name of the name of the column in the data frame, this dot column here type of thing, it will just refer to that. Another way of notating this is just like we have up here, right? Except I'll want to use a string because I'm referring specifically to the column itself. So this is exactly the same as the dot notation. It doesn't matter which you use. The one drawback with the dot notation, though, is if you have any spaces in your column names, you have to do it this way. You have to do it with the square brackets. You can't use it in the dot notation. But because survive doesn't have any spaces in it, we can do it this way, and that's perfectly fine. So we have our X defined, we have our Y defined. Go ahead and run this. And let's just look at X and Y, right? It never hurts to kind of peek into the things that you're creating, right? We can see that it's just a snippet of part of our data frame, the class, the sex, the age, whether they embarked at Q or S. If it's 0 for both, then we know they embarked at C. Okay, and then we want to look at our Y, and our Y is just going to be a series of zeros and ones. That just tells us whether that index, the passenger at that index survived or didn't survive. Let's see here. Which version of sklearn are you using in Colab? Yes, plot confusion. That's a very recent thing we've been dealing with. I actually just updated some curriculum, and it's man, what is the new thing? It is, hold on here. Confusion matrix. Live coding is always fun. Confusion matrix display. There we go. Yeah. So I might play with that if we get there and it causes an error. It might only just raise a warning though, so we might not have to change anything. But that's a good call out. Okay, so we have our X, we have our Y, and now we're going to call our decision tree classifier. If you remember, this isn't something we had to write by hand. We called sklearn.tree and we imported the decision tree classifier from it. And we ran it. We didn't do any tuning. Max depth, this kind of tells how many nodes that you want to go, like how deep you want to go. We put none, so there's no limit on that. And then random state is basically just like, there's a random component to decision trees, but sometimes you need randomness to be repeatable, right? So imagine pulling a 5-card hand out of a 52-card shuffled deck, but you want to be able to refer to that same 5-card hand every time. So you write it down. That's essentially what the random state does. It acts as a seed. So it'll pull a random state, but it'll be the same state anytime you refer to it at that seed. So if we change this to 0, it's going to be slightly different. If we change this to 42, it might be something else. You can put any number you want here, and that's going to be a seed used for the randomness that decision trees use. And that will kind of change your outcome. But if you, for experimental purposes, if you need that randomness to be repeatable, that's where you'd set that random state. You're setting that seed so that you can take advantage of that. And we can see here that this creates this huge, crazy tree. It's hard. We won't zoom into this because there's a lot of information here, but you can see all these like kind of little nodes and edges. And we have all these different paths, and we have all these many different leaves. So just like we saw in the kind of simplified tree model, each one of these is a question that we're asking. Is it this or is it this? If this, go here. If that, go here. And you go to the next decision. If it is it this or is it this, right? And these might be related to the passenger's age, their sex, their class, whatever the case is. The algorithm has kind of made this huge tree. Now, this is probably going to be suffering from some overfitting. And I think that's one of my next slides here. So, oops. Yeah. I have a link in here to Wikipedia about overfitting, and it also covers underfitting. That's why only overfitting is linked. But we have this kind of description here, where if you have something that is properly fit, right, you're going to have like these blue dots that are on the same side as the red dots. That's going to be an example of a false positive or false negative. It just depends on if your red case or your blue case is positive or negative. But this is going to be a false prediction here. And anything that's red on the other side of this line, on the same side as the blue, that's going to be a false prediction as well. And you can see, I mean, we can do some modeling that will capture every single perfect one and make sure that it's exactly on the right side of the line. But the problem is this model becomes way too complicated, and it's trained on the data that you've presented to it. So it's not impossible to say, hey, what happens if I get a data point here that's predicted as red? And I have this huge complicated model that's trying to train too hard on the data I showed it. That's what we call overfitting. And then underfitting is where it's just too simplified, right? It doesn't have enough, the model doesn't have enough information to explain what's actually going on. So yeah, that's kind of the concept of overfitting, underfitting. And when we're looking at something like this, you can kind of imagine all these complicated questions that you have to ask and parse through and go through all this stuff. But it means basically it comes down to the fact that this is too well trained on the data that we input. And if we give it new data, it's probably not going to be right as often as it could be if we did a little bit of tuning. So let me run this again, even though this is kind of showing here. And I'll run this. Okay, so this, yeah, there we go. This confusion matrix things worked. It kind of told us it was deprecated. This is a good take-home exercise. So if you want to update this to the confusion matrix display, this is the documentation to do that. If you like homework and want to take that home and give it a shot, you're more than welcome to. But basically, what this does is confusion matrix tells us the comparison between what the actual label was and what our predicted label was and how often it was wrong. So the true label, if the true label was died, our model predicted died 532 times correctly. And then it predicted survived when the actual value was died 17 times incorrectly. And same thing here, right? It predicted it died when the passenger actually survived 72 times, and then it correctly predicted when the passenger survived 270 times. So not too bad, right? We're kind of seeing these things mostly getting it right. We have a couple of cases where it's getting it wrong. It seems to be much better at predicting whether a passenger died or not. Actually, no. I think it's better at predicting survive, because 17 out of 270 is going to be a smaller ratio than 72 out of 532. So it's going to err on the caution of survival. And this is where we get into false positives, false negatives. I'm not going to go too in depth with that, but because it depends on how you decide your case, right? If you assign survived as a positive case, then we would say that this is our false positives and this is our false negatives. We'll go ahead and print our metrics. So that was the method or the function we wrote above. We're going to pass in our true Y values and then our predictions based on our input. And we can see that it's about 90% accurate. Our precision is 94%. So this isn't the case where you care more about false positives, you'd want to use precision. In the case where you care about false negatives, you would want to use recall. Not a great score here, though. It's only about 79%. Our ROC AUC score. Now, the ROC AUC and the F1 score, these are a little harder to interpret on an individual model basis, right? If I say, hey, this is 99% accurate, everyone kind of has an intuitive understanding of what that means, right? Out of 100 attempts, 99 of them hit. In this case, only 90 of them hit. But accuracy is, you can just look at that, you can interpret it. It's a very easy thing to interpret. The ROC AUC score and the F1 score, this area under the curve and looking at the rates of false positives, false negatives, it gets a little harder to interpret. F1 score, this is the harmonic mean between precision and recall. I'm not going to get into what that means. You can look it up, of course, if you'd like. There's tons of great YouTube videos that explain this. I highly recommend StatsQuest and Crash Course. But the F1 score and the ROC AUC score, these are metrics that are more helpful when you've run multiple different models, right? Let's say I ran a decision tree and a random forest and some other algorithm, and let's say all their accuracy, their precision, and the recall are all very similar. I can then look at the ROC AUC score. I can look at the F1 score between all three of them and say, hey, which one's higher? that's the one that's going to be better. So these are more comparative metrics rather than kind of individual metrics. Ray asks, is there a metric that one can use to see if the model is overfitting or underfitting? Yeah. So that would be comparing like the ROC, AUC, and the F1. Or you can kind of look at, if you look at your precision, your recall, and they're wildly different from your accuracy, then you'll probably have some overfitting or underfitting. In this case, our precision is high, our recall is low, and our accuracy is kind of definitely further from the recall score. So we would look at this and we'd say it's overfitting, right? It's just a little more, it's creating a model that's too complicated, and think of it this way, right? Overfitting is when, if you take a test and you have all of the answers and you just put the answers in, and then your teacher is like, hey, I'm going to give you an additional 30 questions and I want you to answer these. And then you go, oh no, I didn't really learn anything. I've just been writing down the answers because I know them. Now I don't know how to actually generate that information. So there are metrics, or there's ways you can interpret metrics that'll tell you whether it's overfit or underfit, right? If you run it and you get an accuracy of 100%, that's a red flag that your model is seriously overfit. Alexander asked, when you shuffle the data set and split it into train and test, which we don't do here, but that is an important step, is doing the train test split. You get an almost 50-50 accuracy for predicting survive with this algorithm architecture. Do you recommend splitting into 3 data sets, train, dev, and test for decision trees? It depends on how much data you have. This is kind of a toy data set. We only have 891 passengers here. So you don't really have enough to do, you don't even really have enough to do a train test split here. And that's kind of why we don't do it. It's more or less like a toy example. But ideally, yes, you would want to train, test, split your data. So a typical ratio is like 80% of your data for training, 20% for testing. And what the testing does, you're holding that back from the model itself, right? So it's just learning on the training data. And then once the model is trained, then you show it the actual X values from the 20% that you held out, and then it's going to give you a bunch of Y values that it's predicting, and those are the Y values that you would want to compare with your true Y values that you kind of hid from the model, right? So you have 20% of those Y values the model has not seen. You give it that X value once it's trained, that remaining 20% of X values once it's trained, and it's going to give you 20% of those Y predictions back, and then you have something to compare, and then you can measure how wrong your model was. If you do a train test dev split, or sometimes it's called a train test val or evaluation, or there's different language for it. But basically what you're doing is you're taking that 20% of your testing data, you're holding out another 20% or so, and you're leaving that all the way to the end. So if I have a job where I have to evaluate like 5 or 6 different models and do a bunch of different tuning for each of those models, I would use my test data to evaluate that while I'm going through that process, get those metrics, and I would find maybe the best 2 performing models with their best tuning. And then I'd use my holdout set to compare those 2. And then I would take the metrics from my holdout set or my val set or my dev set, right? That kind of smaller portion of data that I held out, and then take the metrics on that, right? So it's kind of like 2 layers of hidden data. So you know that you're not dealing with any data leakage that's going to give you overfitting or underfitting or anything like that. Great question. Going back to decision trees versus regression, don't decision trees always have more degrees of freedom? That was the word I was trying to think of. Degrees of freedom. Yeah. That was the technical explanation that I couldn't conjure up. But yeah, so the whole talking about the S, the Q, and the C, why we didn't need that 3rd column, it's because we have 1 degree of freedom. We don't want to add in additional information so that we don't have to deal with overfitting. And let's see here. Then regression of those decision trees are more likely to fit with more false positive. Yeah, that's correct, right? If you were to leave in that extra data, you would be more likely to overfit because you're duplicating information, even though it doesn't seem like it because it's not there presently. But the fact that it can be derived from the other 2 columns, and then you're providing that information again, it would be likely to overfit. Perry asked, are we going to get a recording of this meeting? Yes, I believe Corey said it was like 3 business days or something like that. So yeah. Okay. So we have this confusion matrix. We can use that to kind of determine how bad our model is and if it's usable. We have some metrics here that we can interpret, and let's do some tuning, right? All we're going to change here is I'm going to go from max depth 1 to max depth 3. And that means you're not going to have to ask more than 3 questions to get to a leaf. Of course, I pass in my X and my Y. I'll go ahead and plot my confusion matrix. And it looks like it got worse. Yeah, so my accuracy tanked, my precision tanked, my recall tanked, my ROC, AUC tanked. Yeah, I mean, all these dropped like 10%. But it's a simpler model. So this might be something you would consider underfit. Let's see, what is this? Compute the feature importances. Okay, so yeah, this is the feature importances. This uses the Gini index. And basically what this says is what weight is each of these features having on the model. So, you know, you can go back to the early 1910, what was it, 1912 or something, Titanic sank, you know, women and children first, right? It looks like the biggest thing is going to be the sex of the passenger. The class has kind of the next influence, and then the age seemed to have less, right? And I can imagine they're probably, you know, they're definitely going to be more adult passengers than child passengers. So that the age kind of had some influence, but it didn't have a huge influence. And where they embarked from seemed to have mattered almost not at all. So the biggest strategy to survive sinking the Titanic is being the right sex, which I'm assuming was going to be female. So yeah, that's decision trees. Kind of very brief introduction in a nutshell. Again, we talked a little bit about overfitting, underfitting, how you can look at metrics to interpret that. How are we doing on time? I think we're getting close to about 15 minutes. So yeah, we've done some light tuning. We have these decision trees here, and you can kind of see how this works, right? So it's going to ask the question, and I'm pretty sure these are going to be ordered by feature importance. So the thing that has the biggest influence on the model is going to be your first question, right? And we encoded this as 0 and 1. Again, mathematically, it doesn't matter. You can encode it either way. It might change the direction that the tree itself goes, but it's not going to have any kind of like mathematical influence. All this is asking is if it's less than 0.5 or more than 0.5, because we defined female as 0 and male as 1. If it's less than that, if that's true, that means that it's a female passenger. Then you want to ask what class they're in. And because it's class 1, 2, and 3, if it's class 1 or 2, so if it's less than class 2.5, if it's class 1 or 2, if that's true, then you're going to go here. If that's false, you're going to go here. And then the next thing you need to ask is the age. And how did they represent the age here? I don't exactly remember. I think that was, it's age in years. I guess the important question is if it's under 2.5 and it's true, then you are likely to survive. So basically, all the toddlers survive. But you know, if you're an adult, it kind of relied on your gender, and you know, yeah. And we see these Gini values here. Again, I won't get too technical with that. It also tells you the number of samples that it considered. So, for example, we can see that this goes from gender or for sex female. If it's true, then we get down to 314 samples, and we have to ask the class question, right? And then we look at the age, and it tells you how many samples are in that group after you've asked that question. And then there was about 577 samples for males. And then you kind of go through and you ask those questions. So that's kind of how you interpret these. Let's talk about some of the advantages and disadvantages. Some of you had questions that relate to this. So they can be used for regression or classification. They can be displayed graphically, which is a huge plus, just like we kind of analyzed that decision tree going through. You know, again, maybe we can still make something productive or make money or save time or whatever, even though our metrics got worse. Sometimes it might be better to have a more navigable graphic than it would be to have a model that's less underfit, right? Or that has a better fit. So again, all models are bad, but some are useful. And sometimes the visualizations are more useful. Sometimes the modeling is more useful. You have to make all those decisions kind of based on what your application is and what your data is. they're, again, highly interpretable, right? You can print them out, you can follow those nodes, and you can ask questions of it and say, oh, in this case, we have this, in this case, we have that. They can be specified as a series of rules, right? So if you maybe need to write policy for something, you can gather a bunch of data, you can use a decision tree, you can create an edge and node graph to represent that tree, and you can write policy from that. Because you have a set of sequential questions that you need to ask. And that makes it a little easier for humans to make decisions. It tends to be very fast. It's an efficient algorithm. The features don't need scaling. You can scale them, but you don't have to. They automatically learn feature interactions. So looking at things like feature importances and what features have the strongest influence. They tend to ignore relevant features. So you kind of saw that the less relevant questions ended up closer to the bottom of, or closer to the leaf nodes of the tree. So the most important questions tend to rise to the top. The least important questions tend to go down to the bottom. And then they're non-parametric. So it's going to outperform linear models if the relationship between features and response is highly non-linear. So again, it's a non-linear model. If you're dealing with a non-linear system, it's going to perform better than a linear or parametric model. Let's see here. Disadvantages. Their performance is generally not competitive with some of the better, more modern supervised learning methods, although most modern supervised learning methods are ensemble methods. So you can think of things like decision trees and KNN or k-nearest neighbors, or any of these other algorithms, fundamental machine learning algorithms. These are like the primary colors of machine learning. They all have their pros, they all have their cons. But with ensemble models, what you can do is kind of take the best of different algorithms that you need, and you can kind of blend them together. And that's what most modern machine learning is. And so decision trees are a great fundamental model, but they're definitely better performing ensemble methods that you can use that will get you better results. Of course, you also need a lot more data. We only have 891 rows here, so there's some limitations with that. Small variations in the data can result in a completely different tree. So they're kind of very sensitive. They have a lot of high variance. Recursive binary splitting makes locally optimal decisions that may not result in globally optimal trees. We kind of talked about how, like, if a subtree or if you're using a greedy algorithm, it can kind of focus too much on a small part of the tree rather than the overall results. They don't tend to work well if classes are highly unbalanced. I don't know if that's true. I think, again, I didn't write this correctly down, but decision trees, I believe, are pretty resilient to unbalanced data, but I'll have to make a note and look into that. And they don't tend to work in very small data. That is true. That's true of most algorithms. Decision trees tend to need a lot of information. And that's why, even with some tuning, we dealt with some overfitting, we tuned it, we had some serious underfitting. Again, we only have 891 rows. A lot of these algorithms are designed to be used with thousands of data points, tens of thousands, millions, stuff like that. We have one in the Q&A. What do the rest of the numbers in the box represent? I might have missed when you asked that. Oh, in here. So I won't talk too much about the Gini impurity here, but the samples are basically how many rows there, and the value are kind of like the range of the value that it was considering. And then, hold on here. I have some questions in chat. Does the algorithm always assume monotonicity, or does that need to be declared for each variable? No, I didn't cover that, and I'm actually not quite sure what that means, so I'd have to do some research on that. Edward asked, another disadvantage of decision trees versus regression is they're easier to interpret and thus easier to implement changes based on findings. Absolutely, yeah. You'll have a trade-off with that, right? Things that tend to be better fit or more accurate, or better metrics, but very opaque, like neural nets are a perfect example of this, right? We can get some scary accurate neural nets, but they are completely opaque in terms of interpretability. But you can have a model that's highly interpretable, but then has problems with overfitting or underfitting. There's a trade-off there. So if you need very transparent modeling, then you would want to stick to something that's more interpretable. Perfect example of this is in finance, right? you're not really seeing a lot of cavalier, wild west neural nets embedding themselves in the financial sector. And the reason why is because when you're dealing with people's money, you need to be transparent. You need to be able to justify your decisions. So you tend to see a lot of more fundamental modeling in things like finance, because we need to be able to look at our models and interpret them. If you can't interpret them, a lot of banks are going to be like, yeah, that's too risky. We're not going to play around with that. And that's not to say there isn't some research done in that realm. But people that make a living being responsible for other people's money, they tend to be very conservative with the decisions that they make about other people's money, and they tend to be unlikely to go off and just try a bunch of experimental stuff and see what that does. So a lot of the people that are using neural nets in finance are usually doing it with hedge funds that are specifically set up for that, where the private contributors to those funds are like, yeah, let's roll some dice. Let's see if we can get out ahead of the market. But you don't see a lot of widespread use in these it's kind of more modern, neural nets and less interpretable algorithms. Let's see, late to the party, and Chancellor can share the link to the presentation. Absolutely, I'll do that again. So this will be the slides. This will be my Zoom tools moved back into my way, and then this will be the GitHub itself. So, and then basically what you'll do is you'll take this URL. And you'll go to colab.research.google.com. You'll paste that in there, and that will allow you to just open this up, and then you'll have this this whole notebook here. Let's see. Ray says, "Oh yeah, absolutely. I'm happy to provide this information. I think it's really important people have access to this stuff and understand it. Very logical course discussing advantages and limitations, and great overall thought about the scientific methods applied to various. Yeah, thank you. I'm glad you could attend. I'm glad you found some use out of it. So with that, I will. Did I already stop sharing my screen? No, I didn't. I just don't remember where I put my tools. There we go. Yeah, there we go. So yeah, that's a very brief and simple introduction to decision trees. Obviously, this topic can get very, very, very deep. But it's a good starting point. It'll give you some language, some things you can Google, some code you can play around with. So yeah, have at it. And I'll stick around for any questions. Actually, I see another one in the Q&A. I answered that one already. Let's see here. Yeah, absolutely. Thanks for all the questions and participation. That always makes these a lot more fun for us presenters. Let's see, what books do you recommend reading about data science? I would recommend, and it's not a very technical book, but I think it's a great example of some uses, and it's free and it's published by Microsoft. It's called The Fourth Paradigm. And you can get a free PDF of it, hosted on Microsoft's website. And this book is a collection of essays about code and data literacy and general applications of big data and all that stuff. And a lot of this is tailored around a vision of a guy named Jim Gray. If you don't know who Jim Gray is, I strongly encourage you to look him up. Wait, not the sports commentator, but the computer scientist. He is a massive founder in a lot of the big data stuff that came before Google, Facebook, and he kind of foresaw that we need better systems to deal with exponentially increasing amounts of data. He's a huge advocate of creating publicly accessible repositories of the data that's used in scientific research. So it's a big goal for reproducibility and things like that. And even to this day, a lot of academic data for research is very opaque. You can't just go access it, although a lot of institutions are better about that. But yeah, so he was a very influential figure early on in data science, and this book is dedicated to him. But basically, these are just a series of essays that are written about kind of applications of big data and research and things that kind of fit that vision of making data more accessible and more useful. and also providing the skills necessary to interpret those things, the academic skills, the technical skills. Unfortunately, Jim Gray mysteriously went missing. He was an avid sailor. He disappeared on his boat. His boat nor his body were never found. This happened very suddenly. The Coast Guard even implemented a lot of primary research that he did that helped them find other people to try to find him, but they were unsuccessful. But yeah, I highly recommend reading this book. It's not very technical. It's very accessible, and it'll give you insights into some general applications being used. If you want some more technical stuff, I highly recommend the author Alan B. Downey. He produces free and open source textbooks, specifically. Let's see here. I'm trying to think of, there's a handful. So Think Stats would be a good place to start. And you can go to his website, Green Tea Press, and see a handful of these. So if you were to work through Think Python, Think Stats, Think Bayes, and Think DSP, which stands for Digital Signal Processing, you would have a lot of what you would need academically to understand data science. Technically, there's more modern tools, and these books haven't kept up with all of that, but they focus more on the fundamentals from an academic perspective. So you're using simpler tools. So those 4 books would be a really, really good start if you want to get more into the technical and academic aspects of data science. Thank you, Sylvia, for linking that. And then I'll link this. It goes to Think Stats, but you can access the other books there as well. And he's got a lot of other great books on Java and C and Complexity and all kinds of cool stuff. So yeah, check those out, and it'll be a good start. Yeah, so Think Stats, Think Python, and Think Bayes, and then Think DSP. So Think Python would probably be best to start with. Think Stats would be good for the next one. Think Bayes, and then Think DSP. All right, we got a couple minutes left, so I will hang out for any additional questions. And yeah, thank you all for being here.
Hey, Mark, I'm sneaking in because Corey's frozen. So I just wanted to say thank you to everybody who zoomed in to join us today. If you've got any further questions about Flatiron School, I'm going to drop the link to schedule a chat with our admissions team. And as a reminder, you will receive a copy of today's presentation within 3 business days after the event. If you'd like to see any previous events, you can head over to our YouTube channel and subscribe. Thank you again. Have a great rest of your day. All right, thanks, Mark. I think I'm going to see if Corey can close this out, because I don't want to kill it without her being able to record it.